Hi guys, welcome back. So in the last video, we had a look at where Simpson's rule actually came from, or I tried to be as brief as I could, but still giving you a little bit of a background into the mechanics. So this video is more going to focus on how we use Simpson's rule to estimate the area of a function. So let's go ahead and let's actually write Simpson's rule in here first. So Simpson's rule states that the integral from a to b of a particular function with respect to x can be approximated using polynomials by w over 3 for one lot of our boundary terms plus two lots of our even terms plus four lots of our odd terms. So this width is going to be equal to the distance. So this is going to be our point for B, and this here is going to be our point for A from here and here. So this is going to be equal to the distance between here divided by the number of strips. So in this case here, it's asking us to approximate this integral from 0 to pi on 2 for sine of x squared dx. So let's go ahead and let's substitute some of these values in here now. So the width of each strip is going to be equal to pi on a. So let's go ahead and let's work out some of these values now for our boundary, our even terms, and our odd terms. So we're actually going to use the formula to calculate this. So what we're going to do, we're going to take each of these and we're going to put in these strips to start off. So now that I put in each of my strips, what I actually want to do is I want to find the values for each of these points, so the top ends of these functions. So for this first value here, we're going to have x is equal to pi on 8. If you're wondering how I got this pi on 8 value, by the way, each of my strips are pi on 8 wide. And so I would start it off at 0. I've added pi on 8 here. I'm going to add pi on 8 here. So that's going to be pi on 4. Adding another pi on 8, I'm going to get pi on 3. 3 pi on 8. And then adding another pi on 8, I'm going to get my pi on 2 value. Okay, so we got, let's find this first value. So x is equal to pi on 8. So we're going to substitute that into our function. And we're going to get a value for our function. So sine of pi on 8 squared. So let's put that into our calculator. So I'm just going to round to 2 decimal places for these ones. And this one doesn't have an exact value. So this point here is going to be at pi on 8 and 0.15. So then I'm going to repeat that process and I'm going to find each of these 3 values here. All right, now that I've got each of these values, and I've drawn these values on the graph as well, I'm going to identify which values are going to be my boundary values, which values are going to be my evens, and which are going to be my odds. So we might actually choose some different colors to do this. Let's use our boundary values here in red. Oh, and you know what I haven't done, of course? I haven't done this first boundary value here. 1 minute. Okay, so now that we've done that one, so we're going to go ahead. This is going to be one of my boundary values. And this here is going to be my other. So the sum of these is going to be b is equal to 0 plus 0.62. So my boundary value is going to be equal to 0.62. I think this may actually be easier to do as a table, if I'm honest with you, but because we've only got 5 values here, it's not too bad. Okay, so let's go in now with this blue color, and we're going to identify our evens. So this was going to be our first one. So this is going to be f of x0. So that's definitely not going to be included because that's our boundary. This here would be equal to f of x1. So again, this is not going to be our even values. This is going to be our value from in the middle. And this is going to be our value for f of x2. So if we keep going ahead and we keep labeling each of these points, we can see here that this value for f of x2, this is going to be our only even that we have. So my even is going to be equal to 0.58. So when we substitute in, we're going to have 2 lots of that. Okay, let's do my odds now in green. And I know some people do have a few issues seeing green. Maybe I should do this, or maybe I should do this in grey actually, because everyone hopefully can see grey. So now we're going to go ahead, we're going to identify our odd values. So our odd values are going to be my f of x1, so that's going to be this value here, and my f of x3. So let's substitute those in. So we're going to have 0.15 plus 0.98. And these are going to make the middle of those polynomial functions that we were speaking about in the previous video. So this is going to be equal to 1.13. Okay, so let's go ahead. Now that we've got our boundaries, our evens, and our odds, we can substitute that into our original function. So I'm just going to rewrite this. Okay, now that I've substituted that into my function, we can go ahead and we can find our solution. So our solution is 0.82 units squared. And with this, I'm not going to write this. I could have written this as a fraction, but the problem with writing this as a fraction, fractions usually representing exact values. I've used a lot of rounding here, so I think even 0.82 would be, privy to some rounding errors. So that's how we find the area under the curve, or approximate the area under a curve, using Simpson's rule. And so this is used generally for things where we have sort of nasty functions, or we have something like an area of a map that we would be trying to predict, or maybe the volume of a hill or something like that. So this is more of an applied sort of idea. And again, because it's more of an applied idea, that's why, again, I've chosen to use a decimal rather than using an exact value. So that's how we use Simpson's rule to find the area under a curve. I hope you've enjoyed, and I'll see you in the next video. Bye, guys.